Hello, everyone. Welcome back to section 5.1. We were left here finding the mean, variance, and standard deviation for a probability distribution. So as we noticed, we already saw this example for the number of heads when two coins are tossed. We know that this is a probability distribution. We saw that it met the three conditions. Now, what we're trying to do is find the mean, the variance, and the standard deviation. And we have formulas for that. So remember that the mean is the same as the expected value. And the way that it's calculated is by summing the product between x and the probability of p of x. So then first we're going to do 0 times 0.25 plus 1 times 0.50 plus 2 times 0.25. And we're going to add those probabilities. So we multiply x times p of x, x times p of x, x times p of x, and we're going to sum those values. So first, we're going to get 0 here, 0.50 and 0.50. So it's 0.50 plus 0.50. We get our expected value or our mean, probability mean, to be number 1, the number 1. This is the mean of my probability distribution of the probability distribution. Okay. Now we want to find the variance. So for the variance, now if we're looking for variance, we're going to be using one of the formulas above. So there's 2 of those. You can pick whichever one you want. You can use this formula or this formula. So let's look at what we're going to do. So to find, here's the example. This is to find the variance here. This is the formula. Be careful because there's a typo here. This should be, the square should be here. So it should be the sum of x minus mu quantity squared times p of x. The same way as you see it down here. This is the correct formula. So this is the correct formula. So there was a typo. So this is the correct formula. For the variance. So the variance is going to take the value of each x and subtract it by mu, the mean or the expected value for the probability distribution. Remember, it's mu because we're looking at a population, not a sample. So it's 0 minus 1 times 0.25, and then 0 minus 1 squared. So there's p of x. This is x times p of x. And then we have x minus mu. Remember that the mean was 1, 0 minus 1 squared, 1 minus 1 squared, 2 minus 1 squared, times 0.5 times 0.25. And then we're going to take the sum of 0.250 and 0.25. That gives me 0.50. That means that when I sum those, I'm going to get 0.50. So the variance, or sigma squared, is going to be 0.50, and the standard deviation is just going to be the square root of 50. So the standard deviation is going to be, if I take the square root of both sides, if I take the square root of 0.5, I'm going to get 0.707, 0.71 roughly. So that would be my standard deviation. And there it is. So there's my mean and there's my variance. My standard deviation is the square root of the variance. And that is my solution for this example. Now, what is the interpretation? Remember, what we care most in statistics is the interpretation. What meaning does this have? That means when you're tossing two coins, the mean of heads is 1. The variance, so the mean is represented by mu, which is 1. So there's going to be the mean of this experiment is that you're going to be landing 1 head most of the time. That's the mean. The variance will be half heads, and the standard deviation would be 0.7 of a heads. Also, the expected value for the number of heads when the choice is tossed is 1, right? We know that the expected value and the mean are the same. So that means that if we collect the data on a large number of scale, most of the time we're going to get the mean of 1 head. That's the interpretation. Now that we know how to find a probability distribution, look at a histogram of a probability histogram, and then we know how to calculate mean, standard deviation, and variance, we want to identify significant results with the range rule of thumb. And we saw this again when we were looking at different values of statistics and what does it mean if it's in the region or below the region. Remember, this was a different one because this was represented by S bar, the sample mean. And then we had a standard deviation instead of the big difference. It was 2S and X bar minus 2S. So what we had before when we were looking for a normal distribution, what does it mean to be normal? We were looking at a sample rather than a population. But remember, when we're looking for a probability distribution, it consists of a parameter that consists of a population. So then instead of being X bar, it's now going to be mu, your population mean. So we found that when tossing two coins, the mean, the population mean, the population mean was equal to 1. We know that the standard deviation is 0.7. We want to use if it's significantly high or significantly low. So then what we're going to do is we're going to look at the range of thumb. Here's we have mu. We have mu plus 2 sigma, mu minus 2 sigma. And if we're looking for use those results and use a range of thumb, whether the 2 head is a significant high number in this matter. So then if we plug it in, if we have our mu to be 1, and we want to say whether 2 is a significantly high or significantly low, well, we have to look at the boundary. So it's going to be 1 plus 2 times 0.7, and then mu minus 2 times 0.7. And this should be 1 right here. So then we're going to calculate what's 1 minus 2 times 0.7. That's negative 0.4. And then this is 1. And then we have 1 plus 2 times 0.7. That's 2.4. So where does 2 lie? 2 lies here. Actually, 2 will lie here, which is not above or below. So 2 is not significantly high. Because what would make significantly high? Anything over here, right? So significantly high would be 2.4 and above, because that's what we did over here. So that's what we found. So based on the results, we conclude that 2 heads is not significantly high because 2 is not greater than or equal to 2.4. Now, identifying significant results with probability. Significantly high number of successes. Now let's look at the differences. Now we're looking at the number of successes. X successes among N trial is significantly high. number of successes if the probability of X or more is 0.05 or less. That is that, so you have, what's the probability of X or more being less than or equal to 0.05. So again, 0.05 is not absolutely rigid. Again, this takes you back into what's significantly high, what's significantly low. Now this one is P of X or less than or equal to 0.05. This would be significantly low. Again, X is the number of successes among N trials. And you would be significantly low if it's the probability of X or fewer is 0.05 or less. That is that X is significantly low number of successes. Again, 0.05 is not absolutely rigid. You can also have values such as 0.01. So either 0.05 or 0.01, same 0.05 or 0.01. Now we also have the rare event rule for inferential statistics. We saw this again as well. If under any given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less or significantly greater, what we expect with that assumption is that we conclude that the assumption is probably not correct. So then there can be a probability, a very small probability of an outcome that can be outstanding. So then we would assume that that conclusion is incorrect. That's the rare event rule. Now, we talked about expected value, which is the same as your mean. And more particularly, we're looking at a population mean, mu. The expected value of a random variable X is equal to the mean. We can therefore find the expected value by computing the sum of X times P of X, just as we do for finding the value of the population mean. Let's look at this example. You have $5 to place on a bet in the Golden Nugget Casino in Las Vegas. You have narrowed your choice to one of the two bets. So you bet on a number 7 on a relay, or craps, you bet on a pass line in the dice game of craps. So you have here a number of successes and a number of failures that we have to consider. Let's look at what they're asking us. If you bet $45 on the number 7 on the relay, the probability of losing, they're already telling us, the probability of losing is 37 out of 38. And the probability of making a net gain of $175 is 1 out of 38. The price is $180, including your $5 bet. So the net gain is 175. Find your expected value if you bet $5 on the relay on the number 7. So first, when we're looking for expected value, we're going to use the formula for the mean population, which is the sum between X times P of X. So the probability of obtaining a 7 on a relay, we're looking for the probability of successes. So the number of successes and the number of failures. So the number of failure is 37 out of 38. The number of successes is 1 out of 38. And the value X, what we're trying to do is we're betting $5. That's the amount. So we would do X would be $5 times 1 out of 38. So then what you have is you have a relay, the probability and the payoffs. Here you start with X, P of X, oops. So let's go back, X, P of X, and X times P of X. So we're going to be separating them by losing, winning, and your total. So the probability on the payouts of betting $5 on number 7 is what we're looking for. That is, for every $5 you bet on a 7, you can expect to lose an average of 26 cents. Because we're looking at, you're losing $5 over here. No, so we're up here. You're losing $5, so losing $5 is -5. That's the probability times 37 out of 38, which is this one. So then you multiply x times p of x, and remember that it's actually going to be the sum, the expected value. So let's remove this part. Okay. So the first thing we did was a table separating the event of losing and winning. X represents how much you win, how much you lose, and the probability of given. So we're just going to be using what we're given here. How much you're betting, the number 7, the probability of losing, how much it is, and the net gain when you do win. And this is a probability when you win. So then when you win, it's $175, but the probability is 1 out of 38. You multiply those quantities. And remember, when you're finding the expected value, you need to sum x times p of x. So we're going to add -0.86 plus 0.60. That rounds off to -26. And you can have negative values for my population mean because in a casino, excuse me, in a casino, you will lose money. So remember, we're looking at an interpretation. So your mean can be negative. Your mean or your expected value can be negative. Now, if we have craps, now we have a different type. We have the losing and the winning. Now we're looking at question B. The craps games, you're looking for, you're losing $5 and the probability is 251 out of 495. Where are they getting that number from? Well, if we come back, this is the probability of losing, and the net gain is 244 out of 495. So then you create a probability distribution there and as a table, and then you multiply -5 times 251 over 495, you get -2.53. And then there's a typo here. There's another one. There should be a positive value. Here, this should be positive 2.46 because it's now you're winning $5. The probability is 244 out of 495. When you add the expected negative x times p of x, and then you add that because the expected value is the sum of x times p of x, we are going to be losing a total of 7 cents. So what does that mean for us? That means that you're better off by playing a craps game because you're only losing 7 cents versus losing 26 cents. So craps, you only lose 7 cents, whereas in the relay, it's 26 cents. You're losing 26 cents every time. That's the probability of losing. And with that, we finish section 5.1. Moving on to section 5.2, we'll talk about a binomial probability distribution, which also contains a few formulas. So the key concept of this section is to focus on a binomial probability distribution and methods for finding probabilities. Easy methods for finding the mean standard deviation for a binomial are also represented. So there's also formulas for mean standard deviation for a binomial. So first, on section 5.1, it was just a probability distribution. Here on section 5.2, we're going to look in depth and we're going to look at binomial probability. So that means two different cases. As in other sections, we stress the importance of interpreting probability values to determine whether events are significantly low or significantly high. That's what we've been doing lately. So what are the conditions, or what is a binomial probability distribution? A binomial probability distribution results from a procedure that met the four requirements. So remember, a regular probability distribution has three conditions or three requirements. A binomial distribution has four different requirements. So the first one is that the procedure has a fixed number of trials in a single observation. So how many times are we performing the operation? The trials must be independent, meaning that the outcome is individual. Trial does not affect the probabilities of other trials. A binomial distribution must have exactly two categories, a success and a failure. So every time we're looking at a study, it must be classified into two different things, success or failure. The probability of successes remain the same in all trials. That's the fourth rule. So we have four requirements. We have a notation for a binomial probability distribution. S and F successes and failures denote the two possibilities. So P of S is a probability of a success. So P of S is the probability of success. And we have P of F, it's 1 minus Q, or the probability of failure. So we have P, the probability of a success. So I'm only going to use P and Q, not P of S, not P of F. I'm going to be using only P and Q, where P is the probability of number of successes. So the probability of success. And then Q is going to be 1 minus P, the probability of a failure for an X number of trials. Now we need the following notation. We need to know what represents what. So we need the variable X, which represents a specific number, the same way as we did for a probability distribution. X is a specific number, but now this is a number of successes in N trials. So X can be a number between 0 and inclusive 0, 1, 2, 3, all the way to N. P is a probability of successes in one trial. Q is a probability of failure in one of the N trials. And P of X is a probability of getting exactly X successes among N trials. So most of the time is if I want the probability of getting exactly 2 successes, it's going to look like P of X equal 2. This is of exactly 2 successes among N trials. So the word success is used as an arbitrary and does not need to represent something good. Either there's two categories, be called success S, as long as the probability is identified as P. Caution: when using a binomial probability distribution, always be sure that X and P are consistent in the sense that they're both referring to the same category being called a success. So we need to be very careful here. What is X, what is P, and what is Q? Let's look at an example. If this determines a binomial probability, yes or no. When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 random selected adults know what Twitter is. So exactly 3 of the 5. So, and the number of trials, excuse me. So the number of trials is 5. We have the probability of a person that knows what Twitter is. So the number of successes is 0.85. The number of failures is 1 minus 0.85, which is 0.15. So in this case, we know that this will be a binomial distribution because it's split it into 2 parts, into 2 categories, success and failure. You know what Twitter is, you don't know what Twitter is. This also has the consistency of a success and failure, and the probability will stay the same throughout. So A does satisfy. Now, if this procedure does result, find the values of N, X, P, and Q, which we already did. N is 5, P is 0.85, Q is 0.15, and X, the number of successes, is 3. So let's see it. The number of trials, 5 is fixed. 5 are independent because they are, it doesn't interfere with other selected adults. Each of the trials has 2 categories. They know what Twitter is, they don't know what Twitter is. And for each randomly selected, the probability stays the same throughout, which is 0.85. So since this does represent a probability distribution, we're able to easily identify N, X, P, and Q. N is 5 out of the total number of adults. We want exactly 3, so X will be 3. There is P and there is Q. Again, it is very important to be sure that X and P both refer to the same concept of successes. In this example, X will be determined to be the people that know Twitter. So the P must be the probability that somebody knows what Twitter is. So therefore, X and P do use the same concept of successes of knowing what Twitter is. Okay. Treating dependent events as independent. So sometimes when sampling without replacement and sample size is no more than 5%, we can say that the selections are being independent, even though they're actually dependent. So sometimes you're going to treat them as independent if the sample size is no more than 5% of the size of the population. We also have a binomial probability formula. We also had a probability distribution formula. So the first method is finding this probability distribution formula, n factorial over x minus n factorial x factorial p to the x times q n minus x. You don't have to memorize it, you can just have it down. For x being 0, 1, 2, 3, all the way to n. N is the number of trials. X is the number of successes among n trials. P is a number of the probability of a success in one trial. Q is a probability of failure if any of the 1 trials are 1 minus Q. So this formula you want to have down on your papers. And it does work for S being 0, 1, 2, 3, and so on. Now what we're going to do is we're actually going to be calculating a binomial probability distribution. So what we're going to do is we're going to use the formula of P of x equals 3, the number of successes. And we have n factorial, n minus x factorial, p to the x, q to the n minus x. Now we're going to be substituting the value of x to be 3, n to be 5, p to be 0.85, and q to be 0.15. And you may use your calculator for this. So n factorial is 5 factorial, 5 minus 3 factorial, 3 factorial, p, which in this case is 0.85 raised to the third, 0.15 raised to the 5 minus 3. So then I can do this side, 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. We have 20 times 6, or 120, over 2 factorial, 3 factorial. 3 factorial is 6, 2 factorial is 2. So here we're going to simplify 120 over 12. We get 10. So then here we get 10 times 0.85 raised to the third times 0.15 squared. And this is what you punch into the calculator. So we want to reduce this combination first. This looks a lot like your combination formula, right? N factorial over n minus x factorial instead of x or r's. Then calculator, I'm going to open up Calculate 84. So here, let's clear everything here. So I'm going to do, okay, I want 10 close parentheses times 0.85 raised to the third, close parentheses, 0.15 times squared, because that's n minus x. And then we're going to select enter. And that looks like it's going to be 0.13817, roughly 14%, if we would want to round up. So let me go back to my screen. And there it is. So then the probability of getting exactly 3 adults who know Twitter among 5 randomly selected adults, it's 13% roughly. We can also use the table, a TI-83, a TI-84, and I'll show you that next time. I'll pause the recording now.